All right. Well, welcome to Track 2, ladies and gentlemen. Sorry for the delay on the startup. And just when I get started with my talk, I have another apology to offer. 20 minutes ago, I RM'd my slides. It's one of those days where, yes, command line doesn't help you. You couldn't control Zedit. So these slides that you see have been put together in the last 17 minutes, and then I ran down. However, however, the demos work, and we will be just notepadding and demoing the talk. So at least I've got everything working, which is good. I hope the VM doesn't evaporate while I present and make me look like a complete monkey. All right. Without much further ado, let's get the show going. So, my name is Saumil Shah. I apologize for screwing up the slides. What we're going to talk about in this next hour is basically my own research on ARM shellcode. This is, some part of it might be new, some part of it might be repetitive, but this is stuff that I've been playing around. I got it working and presentable enough, and this is the first time I'm giving this talk. Off to a great start with the slides being borked. I will publish the slides tomorrow for sure. The code will be uploaded on GitHub. It's just a bunch of ARM assembly files. So with this being said and done, let me just give you an idea about the agenda. I'll just start out with a little bit of background about ARM shellcode, which might be about 90 seconds long. And then I'll talk about the 3 areas that I've been working on ARM shellcode. The first area that I was working was on cache coherency, but this problem has been solved before in several other techniques. So what I'm going to focus upon today is shellcode where space is tight and you have really limited space, and some polyglot tricks that I've been working upon. Why? Because I love polyglots. As you may have known from my previous work, I love to confuse file formats, I love to confuse instructions, I love to confuse scripts, and I love to confuse people. So we're going to see some polyglot tricks. The demos are all working. Okay. The first portion of this talk will be about how to handle shellcode when space is really tight. Okay, before that, the background stuff. ARM shellcode is kind of interesting. It's somewhat like rolling the clock back to 2008, 10 years ago, where x86 shellcode was just maturing. You had additions contributed to the Metasploit framework, you had shellcode archives, people were cutting and pasting code, and sometimes they would backdoor themselves if the kiddies don't know what they're doing. There was that fantastic Apache exploit, which actually added a backdoor root into your own system. Things in the ARM space are like that. There's not too much work being done, or not too much work done in the shellcode space. You can kind of get by with the limited shellcode that's available. By the limited shellcode, I mean the classic execv, bind shell, reverse shell, a little bit of stagers. There is an ARM interpreter semi-working. The challenge with ARM shellcode is it's not like the ARM architecture, especially ARM v6 and 7, is not like Intel. Intel gives you a lot of luxury. You get unaligned memory access for fun and profit. You get cache synchronization automatically done. So you can have self-modifying shellcode. You can have encoders and then decode the shellcode on the fly. All that fun stuff works as is on Intel. Not so much in ARM. Things will work, things may not work. Things work on ARM v7, they don't work on ARM v6, and some variants of ARM v7 don't work with encoded or self-modifying shellcode. So there's a plethora of complexity when it comes to running ARM shellcode on actual hardware. It'll run in QEMU, but not on actual hardware. So the overall goal for all my shellcode research is try to keep the shellcode non-modifying, non-self-modifying. If we could modify the shellcode in flight, then polymorphism and all those tricks would be very easy. You just do shikata ganai or something like that. So all this work is without having self-modifying shellcode. Yeah. So first thing we're going to see is how do we go about dealing with shellcode in tight spaces. The most common approach, as we know from the x86 world, has been the egg hunter. And egg hunter stuff has been around for a long, long time. You kind of split up your attack shellcode in two different memory regions. The memory region that is delivered with the part of the memory corruption exploit, like a stack overflow or a format string bug. The shellcode contained is very, very compact. It's like a small string. The egg hunter code does nothing but searches all your process memory pages up and down, and it looks for a pattern. The pattern is typically a 4-byte value of your choice. And this 4-byte value is checked twice, because first time the 4-byte value can occur in different places. So if these two eggs appear consecutively, then we can say that, okay, the rest of the shellcode follows the egg. So if you're exploiting a web server, you may send the overflow in the URL, and you may send the large payload as a part of the post content. The URL may trigger a stack overflow. The shellcode may be lying on the heap. You need a way to somehow find out where the shellcode is on the heap, because the other area where data is loaded is not predictable. And that's why the egg hunter is important, because it will go and scan through memory for occurrences of these two eggs. Once it finds them at any given location, it will then jump to the shellcode following it. I had animations and everything for this, trust me, but they're all gone. So I have to use the 1,000 words instead of a single picture to deliver this message, right? So the main workhorse component of the egg hunter is a loop. You're looking at page boundaries. Now, it may so happen that in your virtual memory space, some pages may not be mapped. So how do you get around it? If you try to like load memory from that page, you might segfault yourself. So we can't test memory pages from user space virtual addresses. You've got to go to the kernel to test the memory pages. And the best way to do it is via a syscall. So you choose a syscall which doesn't kill you. Don't choose exit or anything like that, because your code will end. But if you choose a syscall which takes a memory pointer and performs some non-destructive operation on it, like check for access or check for permissions or something like that. And if that memory page is valid, the syscall will return you some value. If it is not valid, it will say eno_mem or some other error, but it won't kill your code. So every time you check a page boundary, go make a syscall. If it is valid, then scan through the page for the egg. If not, go to the next page boundary, scan through the page, and so on and so forth. So this is how the whole egg hunter used to work, by repeatedly checking each page boundary with a syscall. And there were choices of syscall. Spoonham and Scape's paper when they were building the Metasploit 2.0 framework, they did a lot of work on shellcode and published some excellent work. So I'm kind of standing on the shoulders of giants over here. I've not really reinvented the egg hunter, but kind of adapted it to modern day exploitation, where I have run into limitations with exploiting ARM IoT hardware devices. So the common problems with the egg hunter, the first major common problem is data execution prevention. Like, let's say you have your memory corruption layout where the egg hunter is on the stack memory and the real shellcode is in the heap. With data execution prevention, both these memory regions are non-executable. We have a solution for that. The solution is ROP chains. We all know what ROP chains do. They're these magic trick stringy thingies, and they will turn stack memory or any memory that you choose into executable memory. I'm not going to drive into ARM ROP chains over here. I'll spare you the agony. We will straight away go to the application of ROP chains. But ROP chains won't solve everything for us. Let us consider the same case where your code is split across two regions. Your memory corruption is in the stack, your ROP chain is in the stack. When you apply the ROP chain, you need to be able to specify which memory region you want to RWX. Or you might allocate new memory and then copy the code over there. For fancy stuff, you need space, but then we are out of space over here. So we have to have some trick where even after the ROP chain, the memory region where our shellcode resides must also be turned executable. So if the ROP chain can help you apply RWX to the stack and your shellcode is in the heap, somehow we also want the heap memory containing our shellcode to be executable. For this, I came up with a slightly clever trick at best. I'm calling it the mprotect egg hunter. The trick is really simple. Remember I told you about the syscall that is used to test the memory pages? Well, this is the syscall. Not only do you test the memory pages, but if it exists, RWX the damn thing. So you kind of, painting the memory pages as you go along. And if you do it long enough, a large part of your virtual address space might be just RWX'd by the end of the shellcode. So this is a quick little demo. I will show you how this game works. Right. My cheat sheet. Okay. So I'll show you two sorry. I'll show you two demos. Let me push up the fonts and see, make it legible. Okay. I have two programs over here to test the stuff. There is the first demo program is called egg break, and the other is called egg victim. Let me show the egg victim first. So egg victim is actually a really simple stunt. You have simulated the shellcode being loaded in the heap with some really ugly string copy code. Just allocating a variable and loading the shellcode, and the egg over here is hack repeated twice. Can you read this all the way at the back, or do you want me to push up the fonts a little more? I can't see you all the way at the back either. All good? All good? Very good. Excellent. It's just my eyesight is bad, not yours. And then here you have the classic Stack Overflow function. So when we overflow this code, we're going to get memory corruption in the stack, but our shellcode is in the heap, and we need to do something to jump to the code. Right. Let me show you the first two attempts. So I have two attack vectors already loaded. I will show you the attack script for the first one. So the first one is your classic stack overflow. Because the memory is not executable, we have to have a ROP chain. So here's my mprotect ROP chain. And once I overflow the buffer, I will invoke mprotect. And after mprotect, I will then jump to the egg hunter. The egg hunter will then go and find out the shellcode that exists in the heap. It ends with this egg called hack. This is what it's going to search. And then once it finds it, it's going to transfer control to it. So this is the attack that we're going to try out first. Let me show you the attack. The other program that I'm going to demo it on is called egg break, which is basically the same vulnerability, but instead of shellcode, I've got breakpoints loaded over here. So we'll halt and we'll be able to check the memory. Okay. I'm going to run this in the debugger first. We will run this. We'll just run this like first classic overflow. Good enough. We're going to crash it. We're going to get control of the program counter. We get control of the stack memory. And if we look at the memory layout, we notice that, oops. If we look at the memory layout from the crash, we notice that the stack is read-write and the heap is read-write. There's no executable privileges given to us. We control the registers. So yes, we do have the program counter in our control. Now when we run the ROP chain, what we're going to see is the stack memory is going to become executable. The heap will still not be executable because mprotect just protects that one region. And then we will invoke the egg hunter and see how the memory pages are marked executable, and we'll then move to the other demo. So let me run this again, this time with just the ROP chain. So here I'm invoking the program with the ROP chain as a payload. We still get a crash. Those of you in my class will recognize PC equal to 48, 48, 48, 48 as my preferred crash point. But at the moment, if we look at the process memory, we do notice that mprotect has done its work and applied RWX to the stack. So the stack is in our control thanks to the memory corruption bug. The heap is not yet in our control. Like if you look at the heap, if I dump the memory at the heap, so here's my egg sitting in the heap. This is the hack. I will dump it as a string. So here's the egg sitting over here at address 11008. And if I check the page permissions of that address, it is still read-write. It is not executable. So if you jump here, you will spectacularly fail. Now, let me show you the egg hunter code. So here's the egg hunter shellcode. I'm going to be publishing it. The egg hunter code right now is 60 bytes long, which is not ideally very compact, but is as compact as I could make it with my limited knowledge of ARM assembly. But I'm sure there's some optimizations possible. So here we start with the main loop. We invoke the mprotect syscall every time. This is the page sizes, and this is the RWX permissions. And every time you invoke mprotect, if it fails with eNoMem, that means there's no page existing, then you kind of subtract it, subtract 12 from it, go back to the loop, increment it to the next address. The moment you exit the syscall loop, you will be having a valid page. And from this valid page onwards, you can test whether the egg exists twice. And if the egg exists twice, then you simply jump to the code following the egg. I'm not going to go into the details of the ARM assembly, but that's at a high level what it does. Now we will switch over to, let me look at the cheat sheet again. Right. So yeah, now we're going to invoke the egg hunter chain, not crash. We're going to run egg break again. If everything works, we will get control to our shellcode in the heap and halt at the breakpoints. So we run the final shellcode, the final egg hunter code, and notice that we're now crashing at these BKPT instructions. These are the breakpoints that we've thrown in. The contrast isn't very favorable on the projector, but these two words that I've highlighted, these are the letters hack, which is the egg. So it went over there. Let me show you the memory first. So if I do the attack string at 11008, this is the pointer to 11008, and we're crashing at 11010. So the string at 11008 is, here's your egg hack, and this is the breakpoint sequence. Let's look at the memory privileges. Now, here's what the egg hunter has done. So after you execute the egg hunter from the stack, it started at the top of the process memory and started painting all the pages RWX until it hit the heap. By this time, the heap is already executable. Now we can straight away jump to our shellcode and make it work. So the last demo will be the same one with the real shellcode execve loaded into the heap. And this should give us and you have a shell. Thank you very much. Okay, so this is half a successful talk. Right? The second half, let's see how it goes. All right. The only few points about the egg hunter is it could have been a little shorter, but I wanted to make sure that there are no null bytes in the shellcode, and it should run as is without much modification. Again, I will publish this code on GitHub just after I get the slides and all working. By tomorrow you should have all the stuff and much better slides published. Okay, so with that done, let us talk about the polyglot stuff. So yeah, we saw the egg hunter work with this trick with mprotect. Now let's look at the polyglot. Now, before we get into the ARM polyglot shellcode, I want to prefix this by saying this is not like polymorphic shellcode. It's very different. It's not like I'm transforming the shellcode arbitrarily to something else. There's no steganography, nothing of the sort going on. But this is a polyglot technique with instruction sets. Now, a lot of work with polyglot instructions has been done before. You can mix architectures like x86 and PowerPC and Spark and all. And there have been universal shellcode starters, code that runs on x86, on Spark, on PowerPC, and automatically switches you to the architecture independent of prior knowledge of what your target's going to be. This trick is somewhat like that, but it's a polyglot within ARM itself. Now, one of the common things you're going to do as a shellcode writer, whenever you're dealing with ARM shellcode, is remember that ARM always has fixed width instructions, 32 bits in ARM mode, but ARM also has a smaller subset of popularly used instructions called the thumb mode, where a thumb is half the size of the arm. Not really, my thumb is much smaller, but if I had a very short arm, then thumb is half the size of the arm. Right. I'm sorry, I just have jokes to offer you, not proper slides. So one of the things we want as a shellcode author to do is we want to write the shellcode in compact thumb mode for two purposes. A, it saves size. It's compact. B, we're free of bad characters. We don't have null bytes. We don't have problematic things tripping us up. And the commonly used instructions are still available in thumb mode, and that helps us a lot. So when you write shellcode, the first thing you want to do is you want to switch from ARM mode to thumb mode. And this is usually a 2-byte trick. You add R1 equal to PC plus 1, branch to R1, boom, you're in thumb mode. And then the rest of the shellcode follows the thumb mode. So this is what I'd been teaching in class, and sure enough, 3 years of teaching in class, somebody is going to pipe up, right? Oh wait, but I can signature this. The moment I hear the word IDS or signatures and any crap like that, I go deaf and I go mad. Like, this is ridiculous. Like, we are doing InfoSec for 20 years and all we depend upon is bloody signatures and updates for security. There's something fundamentally wrong here. Anyway, I will not get into my rant about signatures, but whenever I see signatures, I'm really motivated to defeat them. And not defeat them by just obfuscating it. I'm going to defeat them in style with a technique that, okay, like, yeah, signature this. Here's a whole new class of approach, and good luck signaturing this. That was my motivation for Stegosploit. Yeah, I'm going to put JavaScript attacks as pixels on an image. Now tell me whether this code is bad or good. You know, all this technology depends upon is trying to figure out the intent behind a piece of data. Is it going to do bad shit or is it going to do good shit? Now, if I transform the bad stuff into what looks really good, then you can't tell good and bad apart. And that's why all these technologies fail. So somebody wrote Yara rules to detect this arm thumb switch and catch him. So of course, you have to go one up. I have to go one up. So I did this technique. The second case was pointed to me by Travis Goodspeed, and sure enough, there are some processors, especially Cortex-M processors, which are pure thumb processors. So if I have a vulnerability and I don't know which processor it's running on an ARM processor or it's running on a thumb-only processor, I should be able to hit it with the same shellcode, which means that you have one shellcode which can run the same way whether it started in ARM mode or whether it started in thumb mode. And this is where the polyglot stunt comes in handy. We will have a series of instructions which will end up landing you into thumb mode, and then you can put your regular shellcode at the end of it. Thumb mode is the least common denominator. Every ARM processor will switch to thumb, but if it's an M, Cortex-M, then there's only thumb mode available. And another goal for me was to write it for the lowest common denominator of ARM architecture. So no thumb 2, no wide thumbs. Thumb 2 is like 32-bit thumb mode, which is kind of counterintuitive. It's like, yeah, 2 thumbs, 16 plus 16. So I started the research on this purely upon impulse and intuition. And then, of course, it takes, you then have to involve some background knowledge of instructions and such, and a little bit of lateral thinking. And with this, I'll present to you my techniques on universal mode, halftime, thank you very much. Universal mode shellcode. So basically what the universal mode shellcode will do is, no matter how you start it, it'll always land up in thumb mode. It's like a cat. You throw it from the roof, it lands feet down. I should come up with a nice name. Maybe you can choose a name for me and tweet it out. I'll adopt it before I publish it to GitHub. So the rest of the shellcode is simple. You can, like, at the end of this series of instructions, you can tack on whatever you want, reverse shell, exec v shell, blah, 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 whatever it is. So I have a demo on this. I will show you the construction of the polyglot code, for which I had all the ARM encoding slides, which you know where they are now. Gone, burned. But here, so what we need for the polyglot code is, first we need a very deep understanding of how instruction encoding works on ARM and thumb mode. Fortunately, these are fixed width instructions. ARM is 32 bits, thumb is 16 bits. A single ARM instruction can therefore be split into two thumb instructions. Now, we need to be able to choose carefully what the 32-bit value is, which results into two non-destructive thumb instructions for us. They shouldn't trip up our shellcode. What do we consider as destructive? Branches are destructive. Loading from the memory is destructive. If you don't know the register you're loading from, you might seg fault yourself. Writing back to the memory is destructive. Some push pops, not push pops, but load multiples, store multiples can be destructive. So we want to avoid all of those and then use only a few thumb instructions to do the job for us. The benefit that ARM mode gives you, which is often overlooked in shellcode, is the power of conditional instructions. Every ARM instruction, the most significant 4 bits of an ARM instruction are conditional flags. And if a condition exists, you can trigger the instruction. If the condition does not exist, the instruction becomes a NOP and simply falls through. So what we want to do is we want to lay out a series of steps which will execute or fall through depending upon instructions in ARM mode. But then when you cut them all up as thumb mode, they just fall through all of them without disturbing us. And it's a nice exercise which requires luck and perseverance. With this, let me give you the demo. Now, a large part of this demo is going to be with Notepad. I'm sorry about that again. I apologize. Okay. So let's start with really, really simple shellcode. We'll do like an ARM thumb switch, which is basically the most simplest of them all. So here is code to do an ARM thumb switch. Let me push it up a bit to make it clear. This is whenever you start your code, let's say you're starting in ARM mode, these two instructions will switch you to thumb mode. And then these instructions, I haven't really added real shellcode at the end of it, but I'm just setting R7 equal to 11 just as a proof of concept and then breaking. So at the end of this code execution, you'll get R7 equals 11. Now let's see how this works. Right. I'm going to single step through these instructions. So here are your instructions. You have the ARM to thumb switch, and the rest of it is in thumb mode. If we single step, the first, notice that our mode of execution is ARM mode, the thumb flag is off. The second one, the moment we do the second one, our thumb flag becomes on. So the switch has happened, and now you'll move 11 into R7 and crash. So at the end, your crash has R7 equal to 11. This is the regular version. All right. Now, let's see what happens when we object dump this. So I'm going to object dump, disassemble this code into both ARM and thumb mode. So this is the ARM mode. This is the regular disassembly where you see the switch and it goes on. If I force disassemble this in thumb mode, supposing the processor started in thumb mode, then you see how this 32-bit value E2 8F1001 now becomes two thumb instructions right over here. The first thumb instruction is kind of okay. It shifts the register, doesn't kill us. The second one is a branch that's going to ruin you. The third one over here, so this BX instruction becomes a monster. It becomes like this vector floating point instruction that's this is going to kill us. All the BX instructions, if you look at the encoding, have the second operand, all bits are set to high. So this will always be FF. And if you now cut this word up into thumb mode, then all instructions FF become something thumb 2 or something crazy or something that will kill us. So now as you play with these instructions, you're going to see some restrictions being applied on certain bit fields. And we then got to choose these bit fields carefully. If I run this in thumb mode, it's going to die. So I do one test case, and I will show you what this test case is. The test case is universal mode 1.s. Now instead of 2 instructions, add and bx, I've turned them into 4 instructions. So now I want to use the conditional bits. The top 16 bits should be a valid thumb instruction. The bottom 16 bits should be a valid thumb instruction. The top 16 bits in an ARM instruction are conditional bits and the opcode. The bottom 16 bits are registers and operands. I can choose the registers and operands easily, but the opcodes are kind of tricky. I need the opcode, so I'm going to use the condition bits to tweak the top 4 bits to be able to get a valid instruction. So, and I'm using a pair of instructions. The conditions are now complementary. So if you see, the add has now become an add if not equals and add if equals. One of them is always going to trigger, no matter what the condition is. And the second one, the branch became move PC, R1, move if not equals and move if equals. Again, one of them is always going to trigger. So it's either going to be AC or BD in terms of execution. But what the conditions have done is it's given me the power to craft 2 valid ARM instructions with these bits. Let me show you how this works. So I'm going to object dump this. Normally, this is in regular ARM mode. So here are 4 ARM instructions, and when we object dump this in thumb mode, when we object dump this in thumb mode, I want to draw parallels. So here's the object dump in ARM mode on this side. So this single instruction here has now become these 2 instructions over here. So the add instruction, the add not equals, now becomes two arithmetic shift right instructions. The second add instruction becomes an arithmetic shift right and a logical shift left. This is achieved by tweaking these highlighted bytes thanks to the conditional execution. The problem is with these move instructions, we still have, I mean, these are valid thumb instructions, but these are thumb 2 instructions. These are wide end instructions. I don't want thumb 2 because then that restricts me only to ARMv7. So let me show you how the encoding goes. This is where the slides would have greatly helped. So here's the encoding. If you look at this add instruction, it splits up into the first 4 bytes are conditional flags, then the immediate mode is 0, 0, 1, then the add part is from the 0, 1, 0, 0, that decodes to add. The S is the status update. RS is the source register, so source register is hex is 16, which is a program counter. The destination register is 1, which is R1, and this is the operand, which is decimal 9. Now, this same instruction, the single instruction, when you split it into 2 thumbs, you have an arithmetic shift right. So these bits, these 0, 0, 1, 0, 0 that are highlighted, they become the first 5 bits of the second instruction, which is arithmetic shift right. Then this is like a full shift, 32 bits, so it's equivalent to 0. The disassembler shows you 32 for some weird reason. And this is like shift R1 with R1 itself. So this 1009 becomes an arithmetic shift right instruction. The other one, the 128F, the top half of this instruction up to here, that becomes another arithmetic shift right instruction down there. So this is how you're going to cleverly split it by controlling the condition bits and the registers to be able to get you 2 valid thumb instructions. They will mark up the registers, but they won't destroy the code execution. You're going to lose something. Let's lose the register's value, that's okay. And the other one also becomes into 2 thumbs similarly. So then I kind of went ahead with some more choices. I'm just going to give you this demo bit over here. So then you can try and play with different conditionals. So I have add CS and add CC. So carry set, carry clear, move, carry set, carry clear. So each of these conditional flags, these are 4 bits, so they can have 16 possible values, and they will result into different ones. So I kept on trying. The first ones become AND, and the moves also become AND W. I was trying to get rid of this high F over here, and finally I have universal mode 3, which is the winner. Basically, this AND W will work as well, except that this will run only on ARMv7 architecture. This is non-destructive, this works quite well. If you want to go to ARMv6 or below, then we cannot afford to have wide thumb instructions. This brings me to the last iteration of the universal shellcode stub, which is universal mode 3. So here I could not do the branch by move PC comma some register. So I had to literally push a register and pop it back into the program counter. So the register I'm using is R4, which will hold the next PC relative address. R4 is being pushed on the stack and being popped into program counter. Now in ARM mode, you have something called a register list. This curly braces thingy is a bit field containing which registers are to be pushed or popped. And this is the last 16 bits of the instruction. So we have to choose registers so that there are no null bytes and they don't conflict with us. The order of the registers is also important. You can only have registers which are numerically increasing. So with a lot of tweaking, I figured out that I can push 4 values on the stack but pop only 3, and that's good enough. And this is somehow, if I pop the 4th one, then I got instructions which are not very happy in thumb mode. So this is a lot of back and forth going on. Had to play around with it. So you have add, you have the move. So I transfer the stack pointer into R3 because I got to restore it back. Otherwise, my stack is going to be completely screwed. And then I push the R3 and restore it back into the stack, push the R4, restore it into PC. And again, you have these complementary conditions. So again, you have 1, 3, 5, or 2, 4, or 6 happening. This is going to drop you into thumb mode, no matter what the architecture is, and no matter what mode you're starting in. Let me show you the object dump. Then I will have a small demo to prove that this stunt works. And then hopefully I survive this talk. Sorry. Oh, wait. Yes. Did I do the whole thing with that thing in the middle? Yes, I did. No, so I'll walk you through the object dump in ARM mode. So here's your stub in ARM mode. So R4 is program counter plus relative offset. R3 is stack pointer. Then you push them and pop them back into push R3, R4, pop them into SPPC. I had to have R1 and R8 to avoid null bytes in the resulting thumb instructions. And at the end of this, you should be into thumb mode, and this code should execute normally. Let me force disassemble this. Let me force disassemble this into thumb mode. Now, if you go to thumb mode, it looks quite different. Oops. So in thumb mode, a single add instruction over here is now transformed into and add. Then the next one is also and move. The third one is 2 adds. The fourth one now becomes add and move. The fifth one. So the pushes become LS and subs. I also have the encoding for the pushes that I'm going to show you. So here is how the push instruction is encoded. To give you an example. So push is, these are data transfer instructions, so they're kind of complex. The condition bits are the first 4 bits. Then these indicate 100 over here, I mean 100 means it's load store instructions. The P is for push or, no, sorry, what is the P for? P is for something. I forgot what it is for. U is up or down. This is the forward or reverse. S is update the status flag. The bang is if you want to write back to the base register. And this bit is load or store. So if it's 0, it is store. If it's 1, it is load. So basically, these bits translate to push. That is store with the stack pointer. And these bits imply pop, that is load with the stack pointer. So stack pointer is, this is the base register, which is the stack pointer. R13, yeah, this is R13 is a stack pointer. And this bit field is a 16-bit register list. the bit field starts from the least significant bit. So if a bit is on, that corresponding register will be populated. So this is going to be R1, R3, R4, and R8. This R8 had to be there, otherwise there was a null byte that was creeping up and that was damaging the instruction. And this other one is just pop. I'm only popping 3. And these, they get decoded to a shift instruction and a subtract instruction. The other one, the pop gets transformed to an add instruction and a subtract instruction. So there you have to play a lot with this encoding stuff. And then once you get it right, hopefully this stuff should work. Okay. So as far as the demo goes, I have a test case. So I have the universal test arm.s. This is basically just starting off in ARM mode. These instructions will drop you to thumb mode, which is kind of obvious because that's what they are. I have just placed them as arbitrary shellcode for a test. But let me show you the thumb test, which will be more interesting. So what I'm going to do is, in this test, I'll forcibly switch to thumb mode and then invoke the same instructions, but the code is compiled as code 16, which is, this will be forcibly assembled as thumb mode. I'm just laying these out as literals. Now, what it should do is, all these literals should switch you to thumb mode. While being in thumb mode, keep you in thumb mode, sorry, and then you will XOR R2 and set R7 equal to 11. Okay, GDB universal test thumb. Break start, run. So here we will switch to thumb mode after the first 2 instructions. So I step 2 and so after I step 2, we are now in thumb mode, and the add CS, move CS, and the pushes have now been transformed to a series of and, add, moves, and all these. So if I keep, let me skip 4 instructions at a time. So step through 4 instructions at a time. So the first 4 went through, no problem. The next 4 will go through, and the last 4 will go through. There's more. Yeah, the last 4 are now remaining over here. So if this is non-destructive, all good. Now we are at our proof of concept code. We're still in thumb mode, and if we finish up, we'll get the register 2, which is zeroed out, and R7 is set to 11. So you start in ARM mode, you drop to thumb mode, you start in thumb mode, you stay in thumb mode. The code doesn't change. Now, this is this is like one iteration or one turnout of the code sequence. You can use your imagination, you can use your fluency with assembly, conditional execution, and play with opcodes and get like a large set of polyglot sequences to then drop you into thumb mode. So to the Yara rule maker's signature, that. Yeah. So this kind of brings me to the end. Again, I apologize for the slides. They will be published tomorrow, and the code will be pushed on GitHub. You can play with it. If you find any additional stuff, I know this room has more ARM experts than me who played with a lot of stuff. Please let me know. It'll be great to improve the shellcode and collaborate, or you can fork it or merge it back. It'll be a pleasure to work with you on this. Ideas are most welcome. I'll be tweeting tomorrow when the slides are up. So with this, thank you very much. Thanks for putting up with my semi-broken talk. And enjoy 44Con. And there's a bus full of gin waiting outside. All right. Thank you very much.